Hello, I am Aknur Karabai, Research Assistant at the Institute of Smart Systems and Artificial Intelligence, and in this video we will cover List Absolute Shrinkage and Selection Operator, or shortly LASSO regression. LASSO is a regression analysis method which enables feature selection and regularization of data models. The method was introduced in 1996 by statistics professor Robert Tibshirani. Before we start with explanation of LASSO regression, let's first understand the problem where LASSO regression is usually used as a solution. Let's first understand what is regularization and overfitting. Suppose we are given the data on weight and height of two groups of people, as shown on the graph, and we want to be able to separate and identify the correct group of a particular data sample. The complex line shape shown here accurately separates the groups. But the model here is overfitting the given data and does not generalize well to the unseen data. Now, the line here shows a good stable model for this dataset that we want to achieve. Overfitting occurs when the model fits the training data extremely well but performs poorly on unseen data. There are several ways to overcome overfitting. The first one is increasing the size of the training set. Next is data augmentation. The third one is reducing the complexity of the model. And the last one is regularization. In machine learning, regularization is used to reduce errors by fitting the function appropriately on the given training set and avoid overfitting. To illustrate how does regularization help to overcome overfitting, let's consider linear least squares regression. Least squares method is a statistical procedure that determines the best fit for a set of data points by minimizing the sum of the offsets or residuals of points from the plotted curve. The graph below illustrates the least squares method. The distance between the data points and curve is called the error, and the purpose is to get the minimum sum of squared errors. So the cost function for the least squares regression is as follows: sum of squared differences of the target value and approximation function, where x is the input feature and wi is a function parameter. The cost function measures the error between predicted and expected output values and presents it in the form of a single real number. Loss function evaluates the model by measuring the difference between the predicted and expected value for one training sample. Regularization adds penalty term to the loss function. There are two common regularization techniques: LASSO regression and ridge regression. LASSO regression is a regularization technique that is also referred as L1 regularization or L1 norm. Ridge regression is referred as L2 regression or L2 norm. So what is norm? Norm is referred to a vector's magnitude that defines the length of the vector as a non-negative number or the extent of the vector in space. L1 norm is calculated as the sum of the absolute vector values. L1 norm is a calculation of the Manhattan distance from the origin to the vector space. And L2 norm calculates the distance of the vector coordinate from the origin of the vector space. It is also known as the Euclidean norm, as it's calculated as Euclidean distance from the origin. So in LASSO regression, the absolute value of the coefficients are added as penalty term to the cost function. And it is mathematically expressed as follows. Here, W is the coefficient of a parameter and M is the total number of parameters. L1 norm is multiplied by a regularization term lambda. In case of ridge regression, the squared magnitude of coefficients are added as penalty term to the cost function L. And mathematically expressed as follows. Regularization parameter lambda is controllable and can be fine-tuned during training. For larger lambda, more coefficients are forced to be zero, as model tries to minimize the loss function. And when lambda is equal to zero, then the model becomes the ordinary least squares regression. So now, let's focus on L1 regularization. LASSO regularization allows to set some coefficients to zero, and that's why it allows to neglect some features completely in the estimation of the output. Therefore, it does not only reduces overfitting, but also does feature selection. LASSO regression performs best when the number of observations is low, but the number of features is large. So now let's understand why LASSO prefers a sparse solution on the sample of a linear model. The equation of line is given as f of x equal to w1x plus w0, where w1 is a slope and w0 is y-intercept. Given linear model and adding a penalty term, we get LASSO is equal to the error plus sum of absolute values of parameters multiplied by the regularization term. The diamond shape represents the contour for all possible combinations of coefficients obtained using L1 norm equal to some constraint or constant. The edge shows the sparse solution when one of the coefficients is 0. Well, if we had 3, not 2 parameters, then the 2D diamond shape would become a 3D rhomboid, and we would end up with much more complex shape as the number of parameters increases. For the given linear model, suppose the red circle represents the set of feasible solutions, and the intersection of the circle and diamond shape shows the optimal solution with the smallest regularization term value. In this particular case, we can see that the term W1 is not affecting the output, and we can neglect it. Overall, LP norm where P is less than 1 are good in finding a sparse solution, but they are computationally expensive. But LASSO regression is computationally feasible and has advantage of yielding a sparse solution in which many parameters are equal to 0 compared to large p-valued norms.